We are going to look now into application of integration. Let us just remember by taking an example that integral x cubed dx was x to the power 4 over 4 plus c, with c being any real number. This shows us that practically when you calculate the integral, you don't get a single function whose derivative is x cubed. You get a family of functions. This can be x to the power 4. The derivative x to the power 4 over 4, the derivative of this function gives you x cubed, or x to the power of 4 over 4 plus 1, x to the power of 4 over 4 plus 2, x to the power of 4 over 4 minus 1, and so on. The slope function for each of these functions is the same. It's x cubed. So this was a revision. So now let's look at the area below a function. Let's take a function y equals f of x. Assume that its graph looks like this. Y equals f of x. And we are going to look at the area from below this function, between this function, the graph of this function, the x-axis, and the lines x equals 0, and let's take a particular x here. We will call that area A of x, because it depends on this point x here. So that's why we call it A of x. A of 1 will start from 0 and end up to 1. A of 2 will start from 0 and end up to 2, and so on. So this area is A of x. Let us consider a point after x. Let's call it x plus h. Then the area from x equals 0 to x equals h is going to be A of x plus h. Right? This is a blue area here. The difference between the two areas will be this region here. So the red region is going to be, of course, A of x plus h minus A of x. I am looking for a relationship between the area and the graph of and the rule of y equals f of x. So what can I see for now is that A of x plus h minus A of x, meaning the red area, is when h is very, very small, the red area is approximately equal to a rectangle, to area of a rectangle. So I can say that this is about h, the base of the rectangle, times f of x when h is very, very small. Right? Because this bar and this bar are almost the same, and I can say they are equal to f of x. Meaning that f of x approximates to A of x plus h minus A of x over h. And when h approaches 0, limit when h approaches 0, A of x plus h minus A of x over h is going to be exactly f of x. If you look on the right hand side of this equation, you'll recognize the derivative of A of x by the first principle. So f of x, it is the derivative of a in the point x. Now I know that opposite to differentiation is integration, meaning that I can find A of x. So let us revise where are we left from the previous slide. I started with a positive function y equals f of x, and I found that the area below the graph of the function from x equals 0 and a certain x follows f of x equals the derivative of the area, where this function was called a of x. Now, derivative is inverse to integration. So somehow I can imagine that I will find the area using integration. Let us remember that integral f of x dx, it's a function which I'm going to call it f of x, f capital of x. Let's call it like this. And it's always plus c, because you don't find a single function whose derivative gives you f small of x. This function capital f of x is called the antiderivative of f. Now, going back to my area, if, for example, I need to find the area between, let's generalize, I don't want it just between 0 and x. Let me try to find the area between x equals a and x equals b. Then if a is 0, I will find the particular case above. So I want to find this area. This area can be found by calculating f of b plus c. This is area from x equals 0 to x equals b. Take away f of a plus c. So I need to take away this area, which is going to give me f of b minus f of a. Therefore, a method to calculate the area is integrate f of x, find the antiderivative, and then find f of b and f of a and subtract them. Let us use this in an example. I'm starting with a simple example. Find the area between the graph of y equals x squared x equals 1, x equals 3, and the x-axis. So practically this is the area that I'm going to find. Integral f of x dx is integral x squared dx, which is x cubed over 3 plus c. Therefore, the area is f of 3 minus f of 1. So 3 cubed over 3 minus 1 cubed over 3. 9 minus 1 over 3, 26 over 3. That's the area required. I need quite a few lines in order to write this. Therefore, I have a notation for it. Instead of writing this in 2 steps, I can write that this is an integral from 1 to 3 x squared dx. And then in order to calculate this, you just behave as the limits of integration 1 and 2 wouldn't be there. So integral x squared is x cubed over 3 from 1 to 3. And now I replace 3 cubed over 3 minus 1 cubed over 3. And so on. This is called a definite integral because it has some limits from 1 to 3. And the one above, this one, for example, is called indefinite integral. It doesn't have limits. And its answer is a family of functions. So the answer of an indefinite integral is a family of function, more than one function because of this c. It's called a family because they look the same. The answer for an indefinite integral is a number. As you saw in my previous explanations, I linked the definite integral with the area below a curve. Definite integral is more than area, or is not always the same as area, as we are going to see in the next lesson. It is the same when the function is positive. That's why in my example, already the function was above the x-axis. But we don't, we are not concerned about this now. We are just focusing on the definite integrals, not relating them fully yet with the area. So let me take another example. What is integral from negative 1 to 0, 3 over 4 minus 2x dx. First, I focus at the indefinite integral, and remember, this is an anti-chain rule, let's call it. So it's 3 integral from minus 1 to 0, 1 over 4 minus 2x dx. So it's 3 ln 4 minus 2x over negative 2 from minus 1 to 0 equals minus 3 over 2 ln, when I replace x by 0, I get 4, minus ln 6, so it's 3 over 2 ln 3 over 2. It is useful to look at the properties of the definite integrals, and let us just denote integral from a to b f of x dx as f of b minus f of a, right? Where integral f of x dx is f of x. So capital F of x is an antiderivative of f, and f of b minus f of a is a definite integral. If we add integral from a to b f of x dx plus integral from b to c f of x dx is the same as integral from a to c f of x dx. Proof. As you can see, the first integral is f of b minus f of a. The second integral is f of c minus f of b. F of b and minus f of b cancel, so we get f of c minus f of a, which is integral from a to c f of x dx. So that's how I add two integrals if the upper limit of the first one is the same as the lower limit of the second one. Another property of the definite integrals is integral from a to b f of x dx is negative integral from b to a f of x dx. Proof. The left-hand side is f of b minus f of a, which is the same as minus f of a minus f of b, which is minus integral from b to a f of x dx. So that's how I can swap the limits of integration. And the last property is integral from a to b k f of x dx is k integral from a to b f of x dx, where k is a constant. Proof. Now we know that indefinite integral kf of x dx is k integral f of x dx. And remember, we denoted the second one by f capital, so this is k f of x f of x. Therefore, integral from a to b k f of x dx equals k f of b minus k f of a. So it's k brackets f of b minus f of a, which is k integral from a to b f of x dx. Same as in the case of the indefinite integrals, the constant of the scalar factor goes in front of the integral, and same happens here.